Now we're going to move on and talk about coordinate systems. Up until now, the coordinate systems you've dealt with probably look something like this. X goes in the horizontal or east direction, and Y goes in the vertical or north direction. You might think this is the only way you can create a 2D coordinate system, but you would be wrong in thinking that. In physics, we can change our coordinate system to look like whatever we want. Well, almost whatever we want. You see, if we're referring specifically to a 2D coordinate system, then the x-axis can point in whatever direction we want. That's for sure. But now the y-axis can only point in one of two directions. It can point upwards, like this, or downwards, like this. We're going to assume that it can't point in any other directions that are not at a right angle to the x-axis. We say that the two axes are perpendicular to each other. In other words, the axes are at right angles with respect to each other. So now that's all well and dandy for a 2D coordinate system, but what about a 3D system? Well, it turns out that the way we have our coordinate system defined here, there's only one direction the z-axis can point, and that's, well, it's actually directly at you. It's pointing out of the screen. So if we change our perspective a bit, we see that now the z-axis was pointing directly at you. But how did we arrive at this direction? Two things. First, the z-axis has to be perpendicular to both the x and y axes. So that means it can only point in one of two directions. In this case, it can only point either out of the screen like this, or originally into the screen like this. So which one is it? We determine the z-axis direction using this thing called the right-hand rule. Here's how it works. Imagine you take your open right hand and point your fingers in the direction of the x-axis. Now curl your fingers in the direction of the y-axis. Whichever way your thumb points is the correct direction for the z-axis. Incidentally, this coordinate system we see here is called a right-handed coordinate system. If you want a left-handed coordinate system, then you just use the so-called left-hand rule. In other words, pointing your left hand in the direction of the x-axis and curling your fingers towards the y-axis will give you the z-axis in a left-handed coordinate system. With everything we do, we'll always use right-handed coordinate systems. So if you want the correct z-axis, then you should use the right-hand rule to get it. Once we pick the x and y axes, then we have no choice for the z-axis. The right-hand rule gives us the only direction the z-axis can point in. So choose your x and y axes carefully, because you won't get to choose your z-axis. It'll be chosen for you. Now, moving back to our 2D coordinate system, I want to talk about something else, which is this idea of rotating a coordinate system. You see, rotating a coordinate system in 3 dimensions can get real complicated real quick. So we're going to think about the easier idea of merely rotating the xy coordinate system. Now watch this. What if I rotate the coordinate system tick, 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 like this? Whatever angle the x-axis sweeps through is exactly the same angle the y-axis sweeps through. That might look pretty obvious right now, but trust me, it won't be nearly as obvious later when we actually have to make use of this fact to solve some tricky problems. There's one last thing I want to go over, and that's to just quickly review polar coordinates. Polar shows up pretty frequently in physics, so you want to make sure you have a good grasp of it. Imagine you have some point, here, let's look at this one, 3, 4 in the xy system. If I want to transform this point into the polar coordinate system, then all I have to do is imagine what is the distance from the origin to this point, that's the r part, and then what is the angle that this distance point line thingy makes with the x-axis, that's theta. Well then, what is it? How do we get those two? If we want r, the distance to the point, we need to know x and we need to know y. Knowing those two alone should be enough to give us r. You see, r is just the hypotenuse of a right triangle. And it'll always be a right triangle because by construction, by the way we've constructed our coordinate systems, the x and y axes themselves are always at right angles. So the x and y distance measurements will also always be at right angles. Hypotenuse of a right triangle. Where have I seen that before? The Pythagorean theorem. Given a right triangle, a squared plus b squared equals c squared, where c is the hypotenuse and a and b are the other sides. Applied here, this just means r squared equals x squared plus y squared, or better yet, r is equal to the square root of x squared plus y squared. So now, given x and y, we can find r, but what about theta? Given x and y, we ought to be able to find theta too, right? Let's go back to the right triangle. What do we know about how angles in right triangles work? We have the trigonometric functions. Defined cleanly enough, we have sine of theta is equal to the opposite side over the hypotenuse, or y over r in this case. Cosine of theta is equal to the adjacent side over the hypotenuse, or x over r. And finally, tangent of theta is equal to the opposite side over the adjacent side, or y over x. And this last one was exactly what we were looking for. Taking the inverse tangent of both sides, we're left with theta as a function of x and y. Given x and y, I can use this relationship to find theta, and this relationship to find r. Quick side note about the inverse tangent. If you're working in the second or third quadrant, you'll probably have to add your result from the inverse tangent by 180 degrees, or pi radians. Why? Well, it's kind of weird. You see, the issue with calculators, or at least the one that I'm working with, is that they don't take in any information about x and y specifically. They only care about finding the inverse tangent of some number. Here's an example. Suppose we have the following points: 3, 4 in the first quadrant, -3, 4 in the second quadrant, -3, -4 in the third quadrant, and 3, -4 in the fourth quadrant. What happens when we take the inverse tangents of all these points? That's odd. You would think we would get this, but instead we got this. And it just has to do with the fact that you can't use a single number to encode for any point in 2D space. It's just not possible. The arctangent function, it's not dumb, it just sees the number and takes the inverse tangent of it. What does it care whether the number is -4 over 3 or 4 over -3? To the calculator, they're the same number, but us, we know that their inverse tangents are different angles. The same goes for 4 over 3 and -4 over -3. The calculator sees them as exactly the same number. But we see two different points in the 2D plane. So all I'm getting at here is just be careful. I'm not sure how your calculator handles this, but mine gives the correct value in the first and fourth quadrants, but the incorrect value in the second and third quadrants, or on the negative x-axis side of the 2D plane. In that case, all I have to do is take my calculator's answer for the inverse tangent and add 180 degrees or pi radians to it, and I get the right answer. Note that this inconsistency only happens when you try to take the inverse tangent. The tangent function will always work out fine, it's just the inverse tangent that's funky. Here, watch this. What if I take the tangent of 213 degrees? Okay, now what if I take the inverse tangent of that number? You would think I would get back what I started with, 213 degrees, right? But no, boom. I get back 33 degrees. The true answer for the inverse tangent of this number is that it's either 33 degrees or 213 degrees. My calculator doesn't know, so it just spitballed 33 back at me. I have to be the one to figure out whether the correct answer for the angle is this, or this plus 180 degrees. Okay, side note done. So now what if we want to go in reverse? Given r and theta, how do we find x and y? For that, we need to think back to our sine and cosine expressions. Just doing something as simple as multiplying by r on both sides for each equation gives us exactly what we need. X is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Now, given r and theta, we can find x and y. These will be very useful relations for us throughout our journey into physics, so you want to make sure you understand them very, very well.